Hello and welcome. This is SFU Math 152. Name's Brenda Davison. This is section 9.4, Models for Population Growth. So we're just going to have I think it'll be a fairly short lecture here, and it's going to be about two growth models, the natural growth model and the logistic growth model. We've actually seen both of these models in previous lectures, that where we just sort of stated the solution. Now that we know how to solve separable differential equations, we can actually solve these models and discuss them in a little bit more detail. I think this is actually in some some sense coming at a very appropriate time. We are right now, July 2020, undergoing a very unusual world situation where we've seen growth. We've seen exponential growth. We've actually seen what looks quite to be in some countries like a logistic growth model. So I would like, if you're watching this at the time when it seems particularly interesting, to take a look at the Johns Hopkins website, the the number of cases of coronavirus reported by country. Take a look at the curves on a linear plot. Take a look at the curves on a logarithmic plot, and sort of get a sense of what type of growth we are seeing. And here's a rather, in some sense, sad kind of quote in some sense, but a finite world can support only a finite population, and therefore population growth must eventually equal zero. And another thing that you could look at is the population of the world over time, which is very much an exponential growth curve. And that is going to be our first model here. So that's also interesting to look at. And then you can see how, get a feel for how people are using a variety of different models to look at what's happening now, model that, and then use the model by solving the differential equation in order to get a prediction about where we're going to be in the future. And we are undergoing a situation now where that is being done all around the world on a daily basis to try to figure out what's likely to happen and how to mitigate as many of the problems as possible. Okay, so we're going to look at two models for population growth, but this population growth could just as easily be replaced with, for example, spread of a virus. So we can model things in different ways, and some models are better at describing some situations than others. So let's look at the most basic population growth model. And so here's your model. You look out in the world, you say, looks to me like this is how population growth works, that the population at a time t changes at a rate proportional to its size at any given time t. Okay? So that is some sort of observation. You go out, you look at the bacteria in your dish, or the number of rabbits in your field, or the number of people on the earth, and you say, hey, it looks to me like the rate of change of the population is proportional to the number of people that there are. And that doesn't seem like that seems like a reasonable view. The more people you have, the faster your population grows. Okay, so then what you do, so this part here is not, I wouldn't say, I'm going to say it like this. I don't know if it's the best way to say it. It's not the mathematical part. That's an observation part. It's a looking and seeing what happens. Then you translate what you think you see into a differential equation. Is here, the rate of change of the population is equal to some constant of proportionality times the population. So and after that, everything else like this is mathematics, and nothing is going to be there's no more observation coming into it. We've got a differential equation. We solve the differential equation, and then we make predictions about the future. Should our predictions about the future be lousy, then we wouldn't say that our mathematics here was wrong. If our predictions turned out to be lousy, what we would say is our model needs to be adjusted to fit the real world more closely. We would adjust the model, then we would resolve, and then we would make predictions based on our newer, hopefully better and more sophisticated model. Okay, so this is the most basic population growth model. And the good news for us here is that it's separable. Okay, so we have the rate of change of the population is k times the population, and it's separable. It's a separable differential equation. So good news, we can separate. So we'll do that, and then we'll put everything to do in this case with P on this side. P is the independent variable, and everything to do with T on this side. T is the independent variable. We will do the usual thing we've been doing, and that is integrate both sides. And then neither one of these integrals is difficult, so we immediately write the log of the population is k times t plus c. I mean, we're talking about a population, so this is never going to be negative. Right? It's physically, it's a population. It's never negative. We don't have minus 10 people. So we're just going to remove the absolute values. And we've got P then is equal to e to the kt plus c by exponentiating both sides. And then I'm going to separate using the laws of exponents like that. And then I'm going to rename P naught to be equal to e to the c. You'll see why I picked that P naught as a name, but I'm just renaming that constant. And so that's like a let statement. Let P naught be equal to e to the c. And then I'll rewrite out the solution to my differential equation. It means e to the kt. So now I can predict what my population will be at any time that I like. So long as I know, which I could measure in the real world, I would need to know what that constant is, but it is constant. And I can also see that P of 0, putting in 0 for t, is equal to P e to the 0, which is equal to P naught. Okay, so that is indeed the population at time 0. Okay, P naught is equal to the population at time 0. So we have a situation where we have some population at time 0, P naught, and then under this model, we observe that the population grows exponentially. And of course, this is time 0, this is time. This is population as a function of time. So now if we had some time here, I don't have any idea what the time scale might be here, but well, you know, so it could be like 10 years or something like that. Then we could go up here like that, and we would say, okay, 10 years from now, under this model, we predict this population here. Okay. And then if 10 years goes by and we don't have that population, then we adjust our model. Try to take into account all what we know. Okay, that's the exponential growth model. As you can see, it's not sustainable over the long run. I mean, at some point, it's going up and up and up and up very, very quickly. And you know, either your entire population gets infected and it ends, or you run out of food and your population starts growing, stops growing. So there's a variety of ways exponential growth can end. But the one thing is true about that quote: it cannot continue indefinitely. Okay, next, so we recognize, okay, actually our model is predicting growth just to keep going, and that doesn't seem likely. It's not in fact possible. So somehow we have to adjust our model to try to say, okay, so it might grow exponentially for a while, but at some point it's going to reach some sort of threshold because we'll be limited by food supply or space or some other consideration. So then we increase the sophistication of the model a little bit, and in the next sort of more sophisticated model is what we're going to look at, the next model we're going to look at, and that's logistic growth model. And it's based on these following assumptions. So these are, again, this is not necessarily it's an important part of the problem solving, but it's not necessarily quite a mathematical part, that at least not the part we're trying to learn. This is us looking out and saying, okay, what does actually seem to be happening? That, okay, initially the growth rate seems to be exponential. That's when we have a small population, but after some amount of time goes by, the environment is only capable of carrying a maximum number of people, and we call that the carrying capacity. So we also would expect that as time gets, you know, lots of time goes by, we would reach the carrying capacity of whatever is restricting us from continuing with the exponential growth. So say maybe it's a bacterial culture growing in a petri dish, then it at first starts growing exponentially, but once the petri dish is filled, it's going to stop growing, and the population will stop increasing, and whatever population that is at that time, that is m, the carrying capacity. So if we take those two assumptions, so our last model only considered this assumption. Now we're going to take both of these ideas about what happens when a population grows, and we're going to write those into a differential equation, and that looks like this. Okay, so that is our logistic growth model. At this point, our sort of mathematics kicks into gear, and we have a differential equation that says the rate of our population change is proportional to our population that we currently have, but it's also influenced by how close we are to the carrying capacity. So we will now examine this model and see what kind of predictions it makes. Okay, first thing we're going to do is just make a couple of observations before we solve the differential equation, and that is when is dp by dt equal to 0? So when does a population not grow at all? So we simply look at the differential equation and say, okay, fine, dp by dt is kp times 1 minus p over m, and that when is that equal to 0? And that happens when p is equal to 0 or when p is equal to m. So I mean, if you have, we're saying this is basically, our model is basically telling us if there's no people or there's no population, there's no population growth. That's not that interesting, and it's actually a good thing because that totally makes sense. It's also telling us that when our population is at size m, it also stops growing, which is exactly the condition that we set up. Right? The limit as t goes to infinity of p of t is equal to m. So our model satisfies two reasonable end conditions. Okay, then our next step is to solve this differential equation and give ourselves a value, an equation for p of t, which then we can use to predict the population at any time that we like. Okay, so we are going to do that right now. We're going to take everything to do with p to one side, so that's going to be dp over k. I didn't do it that way. Sorry, I'm going to take everything to do with p over to one side. I'm just not sure which side I put the constant on. I'm going to leave the constant on the right-hand side. So it's going to look like this. P1 minus p over m, and that is equal to the integral of kt, integral on both sides. So I've got everything to do with t on one side. This guy here is what I was waffling around about. This guy can be on either side. It's just a constant. For the purposes of this, I have just simply left it on the right-hand side. So I've got everything to do with the dependent variable on the left, everything to do with the independent variable on the right. And I can easily integrate this that function right there. So I've got that already done. So now I need to take a look at this integral here, and I need to integrate that. So let's do that. This is the integral of dp over p times 1 minus p over m. And what do we see in the denominator? What do I see in the denominator? I see a quadratic function. So I see a rational function overall, and the degree of the polynomial in the denominator is 2. The degree of the polynomial in the numerator is 0. So I can now use partial fractions. Yay, partial fractions. So that is then going to be the integral of a over p plus the integral of b over m minus p. Okay. Yeah. Okay. dp. Let us just. I'm just thinking here. Let's see how this looks. Actually, I can I can fiddle around with this. This looks like this: p minus p squared over m, which looks like mp minus p squared multiplied by 1 over m, and then that is looks like this. I factor out the p, and then I get m minus p times 1 over m, and I'm not worrying about this. So there's where my two partial fraction denominators came from. I'm not worrying about this because that can easily be incorporated into one of the constants, a or b. Okay, so now I do the partial fractions on there, and I get that a times m minus p plus b times p has got to be equal to m. And I'm looking at the linear term, I get an equation. That equation is minus a plus b is equal to 0. And then I look at the constant term, and I find that m times a has to be equal to m, and that means that a is 1, and in fact also that b is equal to 1. Making excellent progress here. And so now I know, now I'm take a look at this integral. I've substituted in a is equal to 1. I substituted in b is equal to 1. And I'm going to integrate this, and that is going to be the log of the absolute value of p plus the log of the absolute value of m minus p. I'm not worried about the constant here. There is a constant of integration here, but I know that I'm putting it together with the other half of my differential equation, and I've already got a constant there. So I'm just, if it makes you happy, I like to make you happy. There, I'll put it there. But I'm not going to need that at all. So now what I'm saying is I've got that the log of the absolute value of p plus the log the absolute value. Oh, something is wrong. Hang on. What is the integral here? This integral here, if I take the derivative of this, I get a minus sign. Folks, there should be a minus sign here. Sorry about that. Okay, so let's fix that here too. M minus P, and that's equal to KT plus C. Okay, so this constant encapsulates all the constants of integration from both sides. Okay, now I use my log rules. P over M minus P, and that's equal to KT plus C. Okay, the population is always bigger than 0, and it is always less than M. We established that at the beginning, so I can remove the absolute value signs because the quantity is always positive. So then I'm going to do that, and I'm also going to exponentiate both sides to get this expression here. And then I do the usual thing. Let's see. Oh, I didn't do that till further along. Okay, now I'm going to solve. Next step, solve for P. Solve for P. To do that, this is the way I did it. And you could stop the video and try it yourself. E to the KT, E to the C, and then I multiplied here M minus P. And then I had to distribute this over M and P, and then add to both sides P plus E to the KT, E to the, let's see, C times by P is equal to A to the KT, E to the C times M. Okay, then I can factor out the P, and I get 1 plus E to the KT, E to the C is equal to E to the KT, E to the C times M. Now finally have solved for P. P is equal to this, E to the KT, E to the C, M over 1 plus E to the KT, E to the C. Now I'm going to multiply top and bottom by E to the minus KT times E to the minus KT. And that will get me, and then I'm also going to do what I maybe could have done earlier, let A equal E to the C, and let P of 0 be equal to P naught. Okay, so let's deal with this right now. P of 0 is equal to P naught. That tells me, in fact, I can plug in T equals 0 here, and that tells me that P of 0 is going to be AM over 1 plus M. Okay, I substitute in T equals 0, and I substitute in, so right here, I do here, P of 0 is equal to P naught, and then that is equal to E to the 0, E to the C times M over 1 plus E to the 0 times E to the C. Yeah, and I change E to the C to A, and I get AM over 1 plus A. E to the C is A. Yeah, E to the C is A. Okay, so this should have been A. Good thing I checked that. Okay, keeping going here. We get then that P of, I'm not coming from here again, P to T is E to the C times M. Now I'm doing this multiplication right here, over E to the minus KT plus E to the C. And that is going to be equal to AM over E to the minus KT plus A. Okay, so I've got a solution for my differential equation, and I know what A is. I can express A in terms of P naught and M, both of which would be given to me. So what does this curve look like? And it looks like this. So it basically in the we have here time, and we have here population. So it looks like this. We have some initial P naught, and if we're below the line, if the population is below the carrying capacity, this is M, the carrying capacity, what happens is the population starts to grow exponentially, and then as it gets close up to the carrying capacity, it I want to try. I want this to look nice. So we get a nice exponential coming up here. I'm still not happy with that. A nice exponential, and then it levels out like that. Okay, so it grows exponentially in the beginning, and then the growth slows, and in fact slows to zero as time gets large. If we were in a situation where the population growth was above the carrying capacity, somewhere up here, for some reason, like for example, if you took a large population of, I don't know, rabbits and moved them all to a small island that couldn't actually support all of those rabbits. Initially, there would be a large number of them, but they were more than the carrying capacity of the island. Then what would happen is there would be an exponential die out until the carrying capacity was again reached. Okay, so it wouldn't be the same. So again, we see that the difference in what happens, the trajectory that the population takes over some time is highly dependent upon that initial condition. So initial condition below the carrying capacity, we have an exponential growth, and then as time goes by, that exponential growth slows and in fact stops. And then if we're above, if our population is above the carrying capacity, it exponentially decreases to the carrying capacity. So those are two models for exponential growth, and that is a short lecture, and that's really, in fact, all that that we have to say about that, because now we have the skill between our knowing how to separate and knowing how to use partial fractions. We can solve both of these models and get a function that is predictive of population growth under those models. Okay, thank you, and I'll be back. Bye-bye.